continue the abnormal transference numbers. It has been found that the solution of cadmium iodide exhibits a marked deviation in transport number with the concentration as shown in the table. As the concentration of CdI2 increases, the transport number is seen to decrease. In higher electrolyte concentrations, the transport number of Cd2 plus decreases to 0 and even becomes negative. The possible explanation for the abnormal behavior may be due to the following reaction in the concentrated solution. CdI2 reacts with 2I minus to give CdI4 2 minus. That is, in concentrated solution, the appreciable amount of cadmium are present as anion CdI4 2 minus. In dilute solution, on other hand, we have CdIO2 gives Cd2 plus 2I minus. Thus, if equal amounts of electricity are carried in opposite direction by Cd2 plus and CdI4 2 minus ions, the transport number of cadmium will appear to be 0. Further, if the speed of CdI4 2 minus be greater than that of Cd2 plus ions, the apparent transport number of cation will appear to be negative. Coming to ionic velocity and ionic mobility. Ionic mobility mu is defined as the velocity of the ion when the potential gradient is unity. Mathematically, U plus can be written as V plus by E by D and U minus is equal to V minus divided by E by D, where E by D is the potential gradient and U plus is found to be equal to lambda plus by Z plus into F, and U minus is found to be equal to lambda minus by Z minus F. Let a volume V of the solution containing 1 mole of the substance be placed between two parallel electrodes d cm apart. The electrodes are large enough to include between them the whole solution. In 1 second, as seen earlier, the total current flowing through these electrodes is given by I is equal to I plus plus I minus, which is equal to N plus V plus by D into Z plus E plus N minus V minus by D into Z minus E. Since 1 mole of the substance is involved, the number N plus and N minus will be related to the Avogadro's constant Na by the expressions N plus is equal to nu plus Na, N minus is equal to nu minus Na, where nu plus and nu minus are the respective stoichiometric numbers of cations and anions appearing in the 1 mole of substance. I is equal to I plus plus I minus, which is equal to N plus V plus by D Z plus E plus N minus V minus B Z minus E. We can replace N plus and N minus to get nu plus Na V plus by D into Z plus E plus nu minus Na V minus by D into Z minus E. It can be rearranged to get I is equal to F by D nu plus Z plus V plus nu minus Z minus V1, where F is the Faraday constant and is equal to Na into E. The molar conductivity of the solution is given by lambda is equal to kappa by C, or which is equal to kappa into V, and volume can be written as area into distance. So, we get lambda is equal to kappa into A into D, or kappa is equal to lambda by AD, where A is the area of cross section of the electrodes dipping into the solution. Conductance of the solution G is equal to kappa into A by D, which is equal to lambda by AD, where we have replaced kappa by lambda by A into D into A by D gives G. G is equal to lambda by D square. According to Ohm's law, the current flowing through the solution or electrode is given by I is equal to E by R is equal to E into G. So, I is equal to E into lambda by D square. We can equate equation number 4 and equation number 1 to get F is equal to nu plus Z plus V plus nu minus Z minus V minus is equal to E into lambda by D square. If the solution is infinitely diluted, then using the Kohlrausch law, the above expression becomes F by D into nu plus Z plus V plus infinity plus nu minus Z minus V minus infinity is equal to E by D square into nu plus lambda plus infinity plus nu minus lambda minus infinity. So, we can write for the cation F by D is into nu plus Z plus V plus infinity is equal to E by D square nu plus lambda plus infinity. V plus infinity comes out to be, we can rearrange to get V plus infinity to be equal to E by D lambda plus infinity divided by Z plus into F, and similarly V minus infinity comes out to be E by D lambda minus into Z minus lambda minus infinity divided by Z minus into F. Defining the term ionic mobility U as the velocity of the ion when the potential gradient is unity, we have U plus infinity is equal to V plus infinity by E by D, which becomes equal to lambda plus infinity by Z plus into F, and similarly U minus infinity, which is defined as V minus infinity by E by D, comes out to be lambda minus infinity divided by Z minus into F. At any other concentration, it follows that U plus is equal to V plus by E by D, which is equal to lambda plus by Z plus into F, and U minus is lambda minus by Z minus into F. Units of ionic mobility will be equal to the meter square second inverse volt inverse. Application of conductance measurements. Determination of degree of dissociation of weak electrolyte is the first application. We can use the formula alpha is equal to lambda c by lambda infinity as given by the Arrhenius equation, where alpha is the degree of dissociation of weak electrolyte. Lambda c is the molar conductivity at the given concentration, and lambda infinity is the corresponding value at infinite dilution. When the weak electrolyte is present in completely ionized form, knowing alpha, numerical value of dissociation constant can be evaluated using appropriate expressions. Second application of conductance measurements is determination of solubility and solubility product of a sparingly soluble salt. The solubility of a salt in the solution can be determined from the conductivity measurements. Since the equivalent or molar conductivity of the solution is given by lambda is equal to kappa by C, therefore, it follows that the concentration of the salt of the solution is given by C is equal to kappa by lambda. In using this expression, kappa used should be that of the salt alone, the value of which can be calculated by subtracting kappa of pure water from kappa of the solution. Kappa salt is equal to kappa solution minus kappa water. If the salt is sparingly soluble, its solubility product can be determined from the solubility obtained from the above equation. We can replace lambda by lambda infinity as the solution will be fairly diluted. There is a numerical based on this which can be done as practice time. Third application is determination of ionic product of water. Kw, the ionic product of water, is equal to the product of the concentrations of H plus and OH minus ions. Since the in pure water H plus is equal to OH minus, therefore Kw becomes equal to H plus square, and concentration of H plus, which is equal to the concentration of OH minus, becomes equal to under the root Kw. The conductivity of the purest distilled water is first determined experimentally, and let it be kappa. The equivalent conductivity of water in infinite dilution is lambda naught is equal to lambda naught plus lambda naught minus. Applying the formula, lambda is equal to kappa into V. The degree of dissociation of water is equal to alpha is equal to lambda by lambda naught. We can substitute both the values of lambda, which is equal to kappa V, and lambda naught, which is equal to lambda plus naught plus lambda naught minus. Alpha is equal to kappa V divided by lambda plus naught plus lambda minus naught. Since volume is equal to 18 centimeter cube in case of water, lambda is equal to kappa into 18, and alpha becomes equal to 18 kappa divided by lambda plus naught plus lambda minus naught. From the dissociation of water, H2O gives H plus plus OH minus. The concentration of H plus is equal to concentration of OH minus, which is equal to C alpha, where C is the moles of water per liter, which is equal to 1000 into density of water divided by 18. Knowing the value of C and alpha, H plus concentration and OH minus concentration are computed, and then Kw, which is equal to H plus into OH minus, is equal to C square alpha square can be determined. Fourth application is determination of hydrolysis constant of a salt. Hydrolysis constant of a salt can be determined from the conductivity measurements. Let C be the concentration of the salt BH plus Cl minus formed from a weak base and a strong acid in the solution. The cation of the salt undergoes hydrolysis in the solution. According to the equation, BH plus H2O gives B plus H3O plus. Let alpha be the degree of hydrolysis, and the concentrations of BH plus and H3O plus in the solution will be C into 1 minus alpha and C alpha respectively. The conductivity of this solution is given by kappa 1 is equal to C into concentration of BH plus, that is C BH plus into lambda BH plus C H3O plus into lambda H3O plus C Cl minus into lambda Cl minus. The concentration of chloride ions is the sum of the concentration of the two cations. So we can write kappa 1 is equal to CBH plus lambda BH plus CH3O plus lambda H3O plus CBH plus CH3O plus into lambda Cl minus. Kappa 1 can be rearranged to get kappa 1 is equal to C into 1 minus alpha lambda BH plus Cl minus plus C into alpha lambda H3O plus into Cl minus. So, kappa 1 is equal to kappa 2 into 1 minus alpha plus alpha into kappa 3, where kappa 2 is the conductivity of the unhydrolyzed salt of concentration C, and kappa 3 is the conductivity of the HCl solution of concentration C. Alternate form of equation 1 can be lambda 1 is equal to 1 minus alpha lambda 2 plus alpha into lambda 3. Lambda 1 is the molar conductivity of the hydrolyzed solution. Lambda 2 is the molar conductivity of unhydrolyzed solution of concentration C, and lambda 3 is the molar conductivity of the hydrochloric acid solution of concentration C. The value of kappa 2 or lambda 2 can be determined experimentally by adding a large excess of the base to the solution, which causes the equilibrium to shift to the left, that is, it minimizes the hydrolysis. Knowing the value of alpha from either of the two equations, the hydrolysis constant can be obtained using the expression Kh is equal to C alpha square by 1 minus alpha. The last application of the conductance measurement is conductometric titrations. The conductance method can be employed to conduct the titrations of solutions in which there is a significant difference in specific conductance between the original solution and the reaction mixture after adding the titrant. The method involves the variation of electrical conductivity of the solution during the course of titration. During the titration, one of the ions is replaced by the other, and invariably these two ions differ in the ionic conductivity, with the result that the conductivity of the solution varies during the course of the titration. The relationship between the chemical reaction occurring during the titration and the shape of the resulting curves have been discussed below in detail. If we have acid-base titrations, first type of titrations which we will consider are strong acid versus strong base titration. Consider the reaction in which a strong alkali, that is 0.1 normal NaOH, is added to a solution of strong acid, that is 0.01 normal HCl. The reaction can be symbolized as follows: H plus Cl minus plus Na plus OH minus gives Na plus Cl minus plus H2O. The highly conducting hydrogen ions present initially in the solution are replaced by the sodium ions having a much smaller conductance, where the concentration of the chloride ions remain constant. Consequently, the conductivity of the solution decreases and continues to decrease right up to the equivalence point, where the solution contains only NaCl. After the equivalence point, the further addition of sodium hydroxide results in an increase of conductance, since the hydroxyl ions are no longer consumed in the reaction. Figure shows the graph produced in the above case. It consists of two straight lines intersecting at equivalence point. The shape of the curve is a V-shaped curve, where the conductance is initially decreasing, and after the equivalence point, because of the increase in the concentration of hydroxyl ions, we get increase in concentration, and the intersection point gives the end point. Second case, we can have strong acid versus weak base. When a strong acid is titrated against a weak base ammonium hydroxide, the first part of the curve is similar to strong acid versus strong base titration. But after the equivalence point, the conductance does not vary so much, as the free base behaves like a weak electrolyte and its conductance is very small. The reaction can be symbolized as H plus ions plus Cl minus ions plus NH4OH gives NH4 plus Cl minus plus H2O. Faster moving H plus ions are being replaced by slower moving NH4 plus ions, resulting in the initial decrease of conductance. The shape of the curve is as shown in the figure. The first part of the curve is same as that of strong acid plus strong base, but in the second part we get almost no change in concentration because of feebly ionized ammonium hydroxide. Titration of weak acid versus strong base. When a weak acid, acetic acid, is titrated with a solution of strong alkali, example NaOH, the reaction proceeds as CH3COO minus plus H plus Na plus OH minus gives CH3COO Na plus H2O. The curve obtained in this titration is shown in the figure below. In this case, the initial conductivity of the solution is low because of poor dissociation of weak acid. The addition of alkali causes not only the replacement of H plus by sodium ions, but also suppresses the dissociation of acetic acid due to common ion, that is acetate ion, and thus the conductance of the solution decreases in the beginning. But very soon the conductance starts increasing as the addition of NaOH neutralizes the undissociated acetic acid to sodium acetate, thus causing the replacement of non-conducting acetic acid with strong conducting electrolyte sodium acetate. The increase in conductance continues right up to the equivalence point. After the equivalence point, the conductance increases more because of excess of hydroxide ions. The shape of the curve can be seen for the strong acid strong base curve, first curve. We can see the initial decrease in concentration due to the suppression of the dissociation because of common ion effect. Then due to the strong electrolyte formation, the increase in the conductance is seen, and then another increase occurs because of the free hydroxyl ions, and this intersection of the two lines gives the end point. Weak acid weak base titration. The complete titration curve is shown in the above figure along with the weak acid versus strong base figure. The portion before the equivalence point is similar to that of weak acid versus strong base due to the reasons as discussed above. After the equivalence point, the conductance remains almost a constant as the free base is a weak electrolyte. Last titration which can be done is of a mixture of strong and weak acid versus a strong base. The important feature of the conductance titration is that a mixture of strong and weak acid can be analyzed in single titration. For this type of titrations, we get two equivalence points. The first is due to the neutralization of strong acid, and the second one is due to the neutralization of weak acid. The first point gives the volume of alkali used for strong acid. The difference between the second and first gives the volume of alkali used for the weak acid, and the nature of the curve can be seen from the figure. We have first end point and then second end point. We can also do a titration, conductometric titration experimentally, as we have done other experiments. The experiment is to determine the normality of acetic acid solution by titrating it conductometrically against 0.1 normal sodium hydroxide solution. The requirements that are needed will be conductivity meter, conductivity cell, 100 ml beaker, 100 ml measuring flask, burette, pipette, funnel, conical flask, acetic acid solution, NaOH solution, oxalic acid, tissue paper and filter paper. Theory is of the titration curve, which we have already studied in the above titration example of weak acid versus strong base. So we can skip this part. Then we can have the procedure, the plot we know, we will get a plot of this type. We have preparation of 100 ml of 0.1 normal oxalic acid solution. We need to weigh the required amount of oxalic acid, transfer it to 100 ml measuring flask, dissolve in distilled water, make up till 100 ml mark with the distilled water, homogenize the solution. Then we have to standardize this given 0.1 molar NaOH solution. We pipette out 10 ml of standard oxalic acid solution in the titration flask, add 1 to 2 drops of phenolphthalein indicator, rinse and fill a clean burette with NaOH solution, note down the initial reading, start adding NaOH to oxalic acid solution taken in the titration flask until the appearance of pink color. Note the final burette reading, repeat the titration to get 3 concordant readings. Conductometric titrations. To carry out conductometric titrations, transfer 40 ml of acetic acid solution in 100 ml beaker, rinse the conductivity cell with distilled water and dry it with the tissue paper. Dip the cell in acetic acid solution taken in the beaker and note the conductance. Add NaOH dropwise, 2 drops of NaOH is added and shake the beaker and note down the conductance. Keep on adding NaOH dropwise and note the readings after every 2 drops. Continue this process until increase in conductance becomes more. Take at least 10 readings and then plot the graph with the number of drops of NaOH on x-axis and conductance on y-axis. Join all the points for initial decrease in the conductance and then join the rest of the points with the ruler. Near the equivalence point, slope change of line changes and we can find out the end point of the titration, and the point where the 2 lines coincide is the equivalence point. Find the volume of NaOH corresponding to the equivalence point and calculate the normality of acetic acid. With this, I conclude my topic of conductance. Thank you.